Welcome back to another HVAC-Engineering-Techie training video. Today's video is on HVAC electrical motors and drives for HVAC systems. This is S-12 in our series of system equipment and systems. Remember, this is the channel that talks all things HVAC, engineering, design, construction, equipment, systems, test and balance controls, and efficiency and performance. And I'd love for you to become a subscribing member. To become a subscribing member, you just have to hit that subscribe button down below. Give me a thumbs up if you like the video. It costs you nothing. It's totally free. It's painless for you, but it does me good. And the reason is because Google uses that to evaluate these videos, which keeps me on the air. So I'd really appreciate it if you become a member, and I do appreciate you watching the videos. So let's get started on electrical motors. So first we're going to talk about electric motors. Just electric motors in general. So first, there's different types of electric motors. We've got AC motors, which are alternating current motors. We have synchronous motors, excited synchronous motor, single-phase synchronous motor, three-phase synchronous motor, unexcited synchronous motor, synchronous reluctance motor, hysteresis motor, asynchronous motor, which is induction motor. It's an induction motor, squirrel cage induction motor, slip ring or wound rotor induction motor, capacity start induction run motor, capacitor start and capacitor run motor, commutator motor, AC series motor, AC compensated series motor, and repulsion motor. And then repulsion start induction run motor. Now all these are motors, and the ones that are in orange, those are the ones we use in the HVAC industry. The black ones are either systems that have been used in the past or systems that are used by industry or appliances or other things that we don't use. DC motors are direct current or brushed DC motors, separately excited DC motor, self-excited DC motor, series wound DC motor, shunt wound DC motor, compound wound DC motor, permanent magnet DC motor, brushless DC motors, which is an electronically commutated motor. An ECM motor is a brushless DC motor. And a stepper motor is a DC, electronically controlled stepper motor is also a DC motor. Now these up here, most of these are used for very small motors, like the brush motor. That basically they separately excited, self-excited DC motor were used for very small motors, but we don't use them anymore. We use a more modern motor. The yellow ones, the ECM motor and the stepper motor, are certainly still used in HVAC. Motor speed. So synchronous motors run at exact pole speeds. So the way motors work, they have a stator and a rotor. Now the stator is a part that's bolted to the frame of the motor and doesn't turn, and then the rotor is the thing inside of it that actually turns. And the stator, the power coming in to the motor goes right to the stator. And then in a synchronous motor, the rotor is fed DC current through brushes on the shaft, and we put DC on the rotor. And what happens is the power comes in, it's cycling on the stator, and that's providing a cycling magnetic field. So the magnetic fields in there, the poles are changing magnetic fields from positive to negative continuously. And the rotor with a DC on it is in a DC motor will actually follow that cycling. And it is the way they're made, it follows it exactly. So if it's an 1800 RPM motor, the stator's locked in. Basically, it can't get away from that magnetic field. It's locked into it, and it will turn at exactly 1800 RPM. And that's one of the differences in synchronous motors run exact pole speeds. If they get off more than 2%, they will stop because they'll lose the field and they will work. So they'll be within that 1-2%, or they won't run. Induction motors have slip between the motor and stator due to the lagging magnetic field. And induction motors is what causes the power factor in systems. It's that inrush current and that slip between the phase angle of the power. And that's why induction motors cause power factor. Slip varies depending on the motor efficiency. And this is a speed table. And this table is the number of poles in the motor. And this is the synchronous frequency, and this is induction frequency. 50 frequency is a European standard, and 60 frequency is a North American standard. So we have these two standards. So for a two-pole motor, The RPM at 60 cycles is 3,600 RPM, and it will always be 3,600 RPM. An induction motor with slip will be down around 3,450 or so, 3,490. This is an exact calculation, but they could be anywhere right around that 3,500 RPM range, not 3,600. If you have a 4-pole motor, which is 1,800 RPMs on a synchronous motor, it's only 1,750, 1,740, 1,750 on a 60-cycle induction motor. So that's why you have those varying amounts of RPMs. And then, of course, a 6-pole motor is only 1,100 RPM. So we can see the difference. Now, we used to use this a lot when we'd go, if we needed a 700 RPM motor, we'd go to a 10-pole motor, and we'd be turning around 700 RPM, which is how we got motors to run lower. I never actually have had one over 10 poles. I guess, they made them, but I certainly never had to use one of them, so I don't know. Nowadays, of course, you'd buy a 4-pole motor and use a VFD and slow it down to anything you want. And that's a little more efficient way to do it. So this is a 2-pole motor. This is a 3,600 RPM motor. You see it has 3 phases, so it's got 3 of this phase and 3 of this pole. So we got this pole, the blue, and then we got this pole in the brown. So that's the 3,600 RPM motor. And of course, what happens, the poles are further apart, but the frequency still changes the same, so the motor has to turn faster. And this is a 4-pole motor. You see it's got 1, 2, 3, 4 poles. 4 poles, 3 phases each. That's what all these are. This makes an 1,800 RPM motor, synchronous, or 1740 motor. And that's a 6-pole, and that's a 8-pole. And you can see how many different poles these have in this motor, because that's what it takes to turn that way. So you can realize that this motor is a more expensive motor than that motor, because it has a lot more things going on in it, and a lot more poles. And it still has the windings, so it has to have a lot more windings in this thing than this one does. So these cost a little bit more. Not a lot, but a little bit more. And that's basics, the difference between synchronous and induction motors. So what are synchronous motors used for? In HVAC, and a synchronous motor would be for very large fan motors now, or very large pump motors. Now, I've had the biggest fan I've ever done is 125 horsepower. It's about 120,000 CFM. It's about 14, 16 feet tall, something like that. It was a big fan. Shaft on it was 6 inches in diameter. It was a big fan. I think it was, if I remember right, it was 125,000 CFM. And the biggest pump I've ever done, I've been involved with, was a 300,000 horsepower pump. Big pump. Definitely a synchronous motor on that one. Sometimes it's hard to tell when you get that big equipment. Or if you had high-speed equipment. Now, most of our equipment is not high-speed. And to tell you the truth, some of the bigger motors aren't synchronous motors at all, but are totally DC motors. I think the biggest motor I ever did was a copper mine, and it had a big mill motor. And I don't remember the horsepower, but I do remember it was like 60 feet long and about 20 feet in diameter, the rotor. And I remember it very well because the manufacturer burnt the rotor up testing it. And it was not a good day for them. Single phase and 3-phase on synchronous motors. Very small motors. They also have very, very tiny motors. And the reason these small motors exist synchronous is because they always go the right speed, and they use them for clocks. So if you have something that's timed, like a gear motor, it has to be timed to special speed, they'll use a synchronous motor because they can always guarantee the speed of the motor. Whereas on an induction motor, slip, depending on the amount of slip, it'll be off slightly. So that's why they use synchronous motors. You may have some of these, but you won't quite know where they're at, but they could be on your job. Advantages: synchronous motors are more efficient than induction motors, especially in high load conditions. Now, synchronous motors maintain a constant speed regardless of load. So not like an induction motor does not like to start under high torque conditions. It'll have a lot of problems, where a synchronous motor does not care. Synchronous motor, well, number one, synchronous motor has to get up to speed some way before it does. But if you have a clutch on it or something, you could speed the motor up and then put the load on it. It doesn't matter. It can accept a pretty high torque immediately, where induction cannot. Synchronous motors produce high starting torque, making them useful in applications that require heavy initial loads. So they're like a conveyor belt or something that starts with a high torque. Synchronous motors can produce power factor adjustment. This is interesting. So a synchronous motor, you can actually adjust them to improve your power factor. So if you have a power factor down around 0.88, 0.86, and you want to improve it, and you have a synchronous motor, you can adjust that motor up to a power factor of 1 or 1.1, and you can actually have it take care of that power factor problem by doing exactly opposite what an induction motor is doing, which is the angle for the use of the induction motor is negative, and then we can make it positive. We can actually change the power factor in building with synchronous motor. Disadvantages: synchronous motors require an external means of starting, such as a pony motor or an auto start mechanism. So a synchronous motor cannot start itself. It has to already be up to speed before it can take over and the rotor can be locked to the field. That's what it takes. So we have ways of starting motors. Synchronous motors, of course, more expensive. Synchronous motors require an additional DC power source, which is more expense. This is a starting circuit. It shows where the main three-phase power comes in and hooks to the field. And then we have a DC power supply and a power contactor. We bring DC power on and attach it to the rotor. Now, the good news is it doesn't take much DC. All you're trying to do is activate the magnetic fields in the rotor. You don't have to actually produce the power. You just want enough power for this rotor to follow that. And so the DC power doesn't take a lot of DC power. It takes a lot of AC power to run the motor, but not as much DC motor to keep the rotor locked to the field. Okay, starting types. One type's a pony motor. Now this is probably a, 300 or 400 horsepower motor. Didn't say when I looked at it. It's a fan, so it's, who knows, probably a high-speed fan at that. The industrial fan, obviously. And it has an induction motor built in on the shaft. So it has a separate induction motor right here. And so when you want to start this thing, you turn this power on, it starts turning this motor, the induction motor starts, and it starts spinning slowly. And it'll bring that up to, once it's up to speed, you energize the field. And then you put DC power onto the rotor, and once it locks, you turn this off. So this motor is just free spinning. It's not doing anything, and this whole system is running this synchronous motor. Now, you notice this is a big motor. This is a little motor, because a pony motor does not have to be near as big as this motor, because it's just running it up to speed. And, normally they would probably have a damper closed, so this is not doing its full torque while it's just starting up. The next one is a pony motor generator, which I got that kind of wrong there, but there it is. So what this has, instead of just a regular induction motor, it's an induction motor generator. So it starts up just like the other one. It parts this up, and it runs this as a motor, runs that up, and when it gets up to speed, it turns this on, turns this into a generator, and it starts making power, which goes to a power supply, a DC power inverter, and it turns it into DC. So now this generator is running to run this motor. So it's providing the DC, so you don't need an external power source, which is pretty clever. Some people that had lots of DC made this a DC motor, so motor generator. So the DC motor, in others, it's an alternator, so it can produce this backward. All right, the last one is a little bit more hard to understand, but it's the one that they normally use. It's called damper winding start. And what it does is a lot different. It has a normal field, like a normal synchronous motor, and it has the normal rotor, and it has the brushes for the DC current going to the rotor. But what it also has, it has on the outside here, it has a bunch of coils running through the rotor, and they're shorted at the end. They've welded them to a plate. And what happens is this field now induces current onto those squirrel cages like it was a squirrel cage motor. It's not. But it acts like an induction motor while it's starting up. So when it's starting up, it powers this up, and this is disconnected, and it powers up this rotor starts turning because it's an induction motor for these pieces. This little piece on top here is induction motor. These coils underneath are the main windings for the rotor. These are these windings on top, which are in the induction motor, or the damper windings. And so once it starts up, then the field here is turned on, the DC, and once the DC locks to the field, it will no longer induce current across these dampers. So then it stops. So now the start function stops. which is a pretty clever way of actually doing it. And this is what most synchronous motors use nowadays to start by damper winding start. So that's a pretty clever way of doing it, but that's what synchronous motors are. How are they used? Best for loads that require high starting torque, such as pumps. Best suited for industrial application, popular for electric vehicles. Most all electric vehicles use synchronous repulsion motors, and we'll get to them in a little bit. I'll show you what they're like. Well, here's one right now, synchronous reluctance motor. Guess that's what we're talking about. So instead of having all these copper windings in the rotor, it has a bunch of special aluminum channels, and it has permanent magnets in between. You can't really see it, but this little black thing is a permanent magnet there. And these are actually magnetic force channels. They channel a magnetic force. And what this does is when the field has this alternating current going through it, it induces magnetic fields on this, which actually cause it to interact with the magnets and make it turn. And this is called a reluctance motor. I'm not smart enough to tell you a whole bunch of details about it, but that's basically what they are. And they all have to have VFDs. They cannot operate like a motor starter. They all have a special VFD that can lock the rotor to this field. So it needs to be a special one. And I think Siemens is the first one that's offering a reluctance motor to the HVAC industry. There are some other manufacturers that are catering to some industrial applications and, of course, electric car application doing that. And it has a special pulse width modulated VFD, and that's why it has to be a special VFD. Not all VFDs are pulse width modulation, and so it can do that. So it's just straight to the motor circuit. Nothing advantages. Synchronous reluctance motors are more efficient than induction motors, especially in high load, high speed conditions. That's why they use them in electric cars. They get instant full torque at 0 RPM. Synchronous reluctance motors reduce high starting torque and can produce high speeds, way over 3,000 RPM. Variable speed through variable volume speed drive. So if you got a speed drive, you can do variable speed. Synchronous reluctance motors have simpler starting circuits requirements than standard synchronous motors. This VFD with pulse width modulation will make them work. They don't need to have another motor to start them. Disadvantage is that reluctance motors are much more expensive. Requires a matched variable speed drive. No big deal, but that's what they are. So you will start seeing some synchronous reluctance motor on projects because they are now out being sold in the industry. Induction motors, that's asynchronous. We have these everywhere. Fan and pump motors, compressors, most common HVAC motors, induction motor. Single phase, 2-phase, and 3-phase motors. Starting circuit for single phase. And basically we have most of them are either capacitor start or capacitor start and run. And then, of course, for capacitor start, a startup capacitor, and you have a switch, which is a frequency switch or a centrifugal switch. And as the motor starts up, this winding is in start. This capacitor goes online and starts with that winding. And as it gets up to speed, that switch opens and that winding goes dead, and the run winding takes over. Same thing for 3-phase, except they don't need the start capacitor because they have 3-phase. They start automatically because of the magnetic field circulating. Induction motors are designed to withstand harsh industrial environments. They require minimal maintenance compared to other types of motors, no brushes, so you don't have to worry about that. They can start without the need for additional starting methods, true. Highly efficient at full speeds, but not at low speeds. Generally lower cost motor, higher overload capacity, true. Disadvantage: induction motors have hard starting and rush currents, so they should be used for systems that start under low torque conditions, like a fan. A fan starts up, there's no air moving for it, so its load is 0. And as you turn faster and faster, you get more and more load, the torque goes up, and that's perfect for an induction motor. A conveyor belt for an induction motor is not a too good idea. Not a constant speed motor, has slip. May have low power factor and low efficiency under light loads. So it's good, a good motor and fairly efficient at full speed. But you start getting lower than full speed, efficiency starts going down. Requires VFD control for variable speed. You can use more poles, but the right way is with a VFD. So direct current motors, brush DC motors we use. Small direct drive fan motors, got brushes inside of them. Constant speed variable speed by voltage adjustments to the armature, decreasing current to the field. Pulse-width modulation will all make these motors multi-speed. We don't see a lot of these anymore, but we used to use them quite a bit. It requires brush maintenance due to limited lifespan. The brushes are just carbon pressing against an armature on the shaft, and they will wear down over time. All the drill motors used to have brushes. Now they're brushless, but now they used to be that way. HVAC uses brushless stepper motors used for control devices such as VV boxes or actuators. The stepper motor is fairly slow because it counts how many times it turns, and it stops and calculates that and then turns. So when you watch a VV box, you'll see it'll just do a little bit and stop and wait, and it'll do a little bit more and stop and wait, and that's why that takes so long. Brushless DC motor is a brushless DC motor requires electronic circuits to control the field staging. So we do have these DC motors. ECM motors use brushless DC motors. We'll talk about those next. Use built-in electronic VFD for control. So they have their own electronic control board for them. So an ECM motors, electronically commutated motor. They're small fan motors. I'm not seeing them used on any pumps yet, but small fan motors. And what they do is they have this motor up here, standard fan motor, and then they have this small thing on the back, which is actually a variable speed drive. And the variable speed drive drives this motor, but they're specially mated to the motor and there's special control configurations. A three-phase motor fed from one phase, typical. Have a single phase coming in. You have this pulse-width modulated drive, and the motor itself is three-phase, so it doesn't need a starting torque or anything like that. And it has a sensor that is actually feeding this pulse-width modulated drive of what to do. And if you're out working with these, you'll notice they'll start and they'll just turn a quarter turn or turn back a quarter turn, and they'll just turn a little bit, and then they'll start slowly gaining speed because they're trying to figure out where they're at and what they need to do. So they start really slow, and then they take off. Advantages: ECM motors are high efficient motors, approximately 20% more efficient than an equally sized induction motor. Much more efficient. They are naturally variable speed, which protects the motor and associated drive components. And part of this efficiency gain is that the variable speed drive makes them efficiency from 20% up to 100%, whereas on an induction motor, efficiency goes down a lot when they start slowing them down. Speed may be set manually by setting on the drive or a speed source signal. So you might have a signal coming in from an HVAC system, tells the motor speed up, or you may have set points. You can run an ECM motor at 70% or 80%, like on a VAV box, induction box or something. You might want to set that manually. Disadvantages: ECM motors are more expensive, obviously. It requires a matched variable speed drive normally built into the motor. May have slow reaction to speed change and requires more patience with balancing. The other little problem I've seen is because the motor is mated to the VFD, buying motors is more difficult because you have to normally just buy the whole assembly, but you can buy the motor separately, but it has to be an exact replacement motor. You can't be switching motor and drive together. They're a matched pair, so you have to buy them that way. So they're a little bit more difficult for maintenance if you need to replace a motor or a drive. Motor general characteristics. Casing type. They come in open drip proof, which means that they have a cooling fan on the inside that sucks outside air across the motor and discharges it on the side of the motor. And those are called open drip proof. They're okay for outside. They just remember that they are open, and if you pour water into them, you'll damage the motor. So those are open drip proof. They're designed for rain coming straight down, but not high pressure hose water be blown into the end of them. Totally enclosed motor means just that. They're totally enclosed. They have a cooling fan on the inside of them. And sometimes they have a cooling motor on the back side of them that blow air across the fins on the outside. NEMA frame number. The NEMA frame basically relates to the type of frame, type of base mount, how they're actually mounted, and the dimensions. And they have two kinds: base mounted and flange mounted. And in the base mounted, there's two kinds: there's resilient or rigid, and those are all referred to in the frame numbers. So if you look at the motor dimensions, this is a standard flange mount. This is a standard frame mount. No, this is the resilient one. This is the flange face. This has the flange face. This one is a base mounted motor. This is a C flange motor. And what they have is they have these NEMA motor series numbers, And across there, this will always, no matter what the manufacturer, the dimensions will be this dimension if it has that motor frame number. That's why when you replace a motor, you always make sure you have the same frame number. It's really kind of important because things don't fit if you don't do that. If you get a different frame number, and where you have problems sometimes is you want to up the horsepower of a motor and you happen to be right on the line and you cross to a different frame size. Now you have a bigger job because it may not actually fit the frame holes of the old motor. You may have to modify a frame because you've gone up in horsepower. So that does need to be checked. Now this is just a sample list. This goes on to 60 or 70 numbers, and I've only got 10 or 12 here, but it goes on down to a 3-inch shaft, and that basically the motor size goes up and up and up. So basically it covers clear to 100 and 150 horsepower motors. Bigger motors are special, and I don't really have that information handy, but when you're working on motors, you always need to understand what the frame size is, what the motor casing type is, what the RPM and the type of motor. So motor controllers, all motors need something to control it. And so we have certain motor controllers to do that. We have manual motor starters, which is like, it looks like a switch on the wall. They're actually not a switch on the wall. They're similar, but they're designed to manually start a motor. Small motor controls, normally fractions of 20 horsepower. You can get them for 20 horsepower, but that's getting pretty large for a manual. I'd probably use a start-stop controller for that. But the 1, 2, or 3 phase functions as a disconnect and a motor controller. Manual motor controllers provide a means of disconnect, start-stop of the motor, and overcurrent protection are made rugged enough to provide thousands of operations. They may look like a light switch, but I guarantee you they're not a light switch because the light switch will arc. Well, when you turn on a motor load, it will arc. So basically we use these motor controllers instead because they're safe. They're guaranteed not to arc for the horsepower rating, and they're designed to take thousands and thousands of operations. So constant speed motor starters. Full voltage across the line starter. So full voltage across the line starter. Across the line starters provide remote or automatic start-stop of the motor. Overcurrent protection via either fuses or circuit breakers used for motors that start with low torque values to limit inrush currents. 1, 2, or 3 phase. Reduced voltage starters. Reduced voltage starters provide a remote or automatic start-stop of the motor. Overcurrent protection via either fuses or circuit breakers used for motors that start with high torque values and use the lower speed to limit inrush currents. So if you have a big motor, and a lot of times the facilities don't like this 100 horsepower motor, you would not start across the line because it will actually have such a high inrush, it'll probably dim all the lights. It'll give us a low voltage in the building. So what we do is we make it a part winding start or reduced voltage starter. So it starts up at one speed, and when that gets to speed, it goes to the main speed, and it keeps the inrush under certain levels, and that's what those are designed for. There's auto transformer starter, a Y delta starter, which is multi-winding starter, electronic soft starters, and we'll talk about those, and all those, remote voltage starter, I got that. Electronic and soft start relays ramp motor speed at startup to limit inrush current. These are really handy, and basically a VFD also does that, but does more. These are just soft starters. That's all they do is do a ramp up and a ramp down of the motor. They do nothing else. Variable speed controllers, of course, 1 or 2 or 3 phase. Variable speed controllers provide automatic start-stop speed control of the motor. Normally use circuit breakers for overcurrent protection. May be used for motors that have low or high starting torque values, since they can be programmed for proper control of inrush currents by varying the motor speed. So VFDs have to be set, have to have certain points set in if they're going to be used for high torque applications. So that's why the VFDs are started by factory reps. They come out and they can change all that stuff if they have to. So this is a manual motor starter. Small switch, looks like a switch on the wall, but it's got a little more rugged case. Small motor control, 1, 2, or 3 phase. Single motor switch, you see it's just a switch with an overload in it. Starts that motor, it's no big deal. We put them on the wall and a piece of flex conduit going over to the motor gets it started. And then there's 3 phase, which are a little bit bigger, a little more rugged. And they have some overloads on the phases and start the phase. Now this is just a motor overload. It's not a circuit overload. The circuit overload is taken care of by the circuit breaker upstream. But it does provide a means of disconnect, provides start-stop motor without arcing, provides overcurrent protection by either amp settings or thermal overloads. Circuit protection provided by upstream circuit breaker. So now we'll continue with manual motor starters or motor controllers. Manual motor starters, basically, you can see they're full starter and they have start-stop button on them. They don't have remote start capability, but they're for local start-stop. 1, 2, or 3-phase. You can see this is a 3-phase motor, and this is the starting circuit for a 3-phase motor. And this is the overloads and the contactors. You press this button, draws in this contactor, brings in the motor. Provides a means of local disconnect. Provides start-stop of motor without arcing. Provides overcurrent protection by either amp setting or thermal overloads. Circuit protection provided by upstream circuit breaker. So this one shows a fuse connection, but it could be fuses or circuit breaker. Across the line, automatic motor starters. So now we have motor starters that start across the line. They come in 1, 2, or 3-phase. It provides a means of disconnect. This is a disconnect switch here on the side. Provides start-stop of motor without arcing. So we have a contactor in here that has a coil in there that you bring in your control circuit and power that coil. And when you turn it on, the drive goes on. When we turn it off, it goes off. Provides overcurrent current protection by either amp setting or thermal overloads. Circuit protection provides by upstream circuit breaker. And here's that standard circuit you see. So this is the disconnect device. Then we have the contactor in here, which has motor overloads, which might be thermal heaters or might be actual amp overcurrent. It has the contactor. And then we have a start-stop buttons. Start and stop button. And then we also have this coil here, which is basically remote start. You close this and it actually does remote start. Closing this coil, closing this contactor. Now, reduced voltage starters are different. Now, this first one is a Y delta starter, more complicated, but upon this, and we're going to go through this, what it talks about. So here's the motor, and the motor's got U1, V1, and W1. It might have been T1, T2, T3, but it comes in. And then you have U2, V2, and W2 on the backside. So we've got 6 wires to this motor. And then it means that this wiring allows us to rewire the field coils in different configurations. So what happens is the first thing, when we go to start the motor, we push this start button down, and it energizes the time difference, time delay relay, energizes it, and it energizes M. So the main motor contactor comes on, and W to energize, causing M and W to both energize. So W energizes and M energizes, but D does not through these switches over here. So these are all contactors. You can see the 3 contactors here, and here's the time delay relay up here. So what happens is, and the disconnect device is upstream on this one. And what happens when we wire it with the M wired and then bring this up here to D, which just wires these 3 together, it puts it in a Y configuration. And when that happens, the motor's running down around 60% speed or so. So that allows us to start at lower speeds, and that means lower current because we have low speed. And it will start up that, and then after 10 to 20 seconds, the TD times out. And when it times out, it closes TD1 and TD2. Contactor W is G energized, this one's de-energized, and D is energized through these circuits down here. So when this one is energized, it now wires it in a delta configuration. So now that runs a motor at full speed. And that the speed variance is strictly because of the windings of the motor. And that means that this motor, when you start it up, it'll start up at reduced current, reduced inrush for 10 or 20 seconds, and it'll go to full speed, and it'll, so basically we're able to ramp up the current instead of bringing it all one time so we don't brown out voltage. Reduced voltage starter with an auto transformer type. It has exactly the same features, but it works differently. So on this one, you see we just have a single motor. We still have the 3 contactors. So whenever we start the motor, we push in the start button, it starts the time delay timer. And the time delay timer causing D1, D2 to close, energizing S1 and S2. So this is S1 and S2. So it closes these 2. And when it does that, it wires the motor such that this voltage here, this is open, these are closed. So it actually puts this voltage down here to these at whatever this transformer setting is. These are 3 transformers. So in this picture down here, you see the 3 transformers down here and the 3 contactors up here and the time delay relay up here. So what happens when this first starts, it starts off the middle winding, which may be about 60% of voltage. and it comes down, and now this motor is seeing this 50% voltage because this is open. So it comes up through here and goes up and comes down this direction, and then these are shunted together. And that starts the motor at low speed. So then this connects all three transformers into a Y production reduced voltage in the motor. After the time's out, 10 to 20 seconds, TD3 and TD4 opens, which de-energizes S1 and S2, and energizes M. So now M is energized, and these two contactors open up, and this is energized, and it's now straight voltage to it, and so now it's running at a full speed motor. So this is an auto transformer motor. The part winding start is more popular, at least I've seen it more often. I haven't seen this one very often, but it is available. Electronic soft starter is a good option because it reduces the inrush current much better. It's not staged, it's just staged. These come in real small sizes, up to 5 horsepower or so, and then as big as you want. They go up to 100 horsepower or a bit beyond. They provide a ramp up in motor speed to limit inrush current by changing the motor voltage over time. And normally, the ramp is adjustable over time. Now, some of these little ones, it's a set in the unit, and some of them have tactical feedback, and you set and have parameters for the inrush limit, and they will do whatever time it takes to get that rush in that limit. So it might be automatic, but normally it's adjustable. Available 1, 2, or 3 phase, requires a starter contactor for start-stop control, because these soft starters aren't actually a starter. They're a ramp-up controller, but they're not a start-stop controller. Manual ramp time adjustment, or some have automatic ramp adjustments. Here's what they would look like. You'd have a motor. It could be 1, 2, or 3 phase. You have a soft start, and you have a regular contactor. So this contactor, the motor starter, starts the motor up. It runs full current to the soft start, and soft start ramps it up over time. And that's the starting circuit using a soft starter. Variable speed drives, variable speed frequency drives. The variable flow fans, variable flow pumps, designed to make constant speed motors variable speed by modulating the frequency of the power motor. So not just voltage, they're changing the frequency of the drive, which allows these. When you look at a fan curve or pump curve, and you change the speed of the motor, you will see that the whole curve goes down or up. It doesn't change the shape of the curve. The shape of the curve stays the same, it just goes down or up, which means the efficiency stays about where it was on the system curve. And this is really pretty simple what they look like. Here's a motor, here's a variable speed drive. They have a start-stop signal coming in to start-stop them, and then they have a speed signal. They need 2 points. They don't just have 1 point, they have 2. The one that start-stops them, and one that runs the speed up and down, so you can control these separately from your control system. If used only for manual speed adjustment, then you have to ground the shaft. What happens in a VFD, they all use IGBTs, or insulated gate bipolar transistors, and what happens is, because digital is not proportional, it can't do a sine wave. It has to do a sine wave like that, it has to turn things on and off many, many times, and changing the voltage of each one of them to kind of simulate that sine wave. Well, what happens is when this IGBT fires, it closes, it spikes up really high and then comes right back down to where it's supposed to be. And this is the voltage that we're looking for, but it'll have this high spike. And what this high spike does is it's a positive charge, and it builds up static electricity on the shaft. And when that static electricity gets strong enough to overpower the dielectric properties of the grease in the bearing, it will micro machine the bearing, and it ruins the bearing over time. Now, if you have an automatic control always changing the speed, you don't notice it because it's micro machining everything. But if you have a constant flow fan and you set it at 1 speed, it will micro machine in exactly the same place every time. I've had this ruin a motor within 3 months. Had a customer that wanted us to put control knobs on his air handling units, so during the winter he could turn them down because he didn't need as much air during the winter, so he wanted to turn them down, save energy, and didn't want to spend the money to put full VAV control because these were constant volume air handlers. And we started losing air handler motors in 3 months, and the reason was because of the shaft protection. To do this, you must put shaft grounds on. You must ground the shaft. And normally we put a little ring right here that has a metal brush that brushes the shaft and grounds it to the ground of the motor. and that way it protects the bearing. But that's what does it, the IGBTs. Now, you can never trust some salesman, some VFD drive salesman tell you, oh, our drive can't do that. It's nonsense. Every drive does it. Now, the higher the frequency of the pulse, the worse it is. So if you have a 2300 frequency drive versus a 14,000 frequency drive, the 14,000 will put more static electricity on the shaft than the other one. Now, you'll see drives that refer to six stage drives, and what that means is that when they go up, they're going in steps, not just one all at one time. They'll go up in steps. And this is a little ring on a motor, and you see that just grounded that shaft to the shaft, and that means that motor will be protected no matter what it does. A lot of people specify a ground ring on every VFD motor. Available 1, 2, or 3 phase motors, and that's basically it for electric motors. I hope that was helpful. It was interesting for me putting it together for you, having played with these motors but never really sat down and checked them all out. So hopefully that was helpful. Really appreciate you watching the videos. I thank you for being part of my channel, and I hope this is helpful to you. And if you need subjects I've not covered, put them in the comments, and I'll get interested in generating a video for you. Thanks. Have a great day. I'll catch you on the next one.